Theorem. Let A be a closed subset of a normal space X and suppose that f from A to closed interval minus 1 plus 1 is a continuous function. Then there exists a continuous function capital F from X to closed interval minus 1 plus 1 such that capital F of X equal to small f of X for all X element of A. That is, we have to prove the existence of a continuous extension of the function small f. We prove the existence by applying Urysohn's lemma. For this, we will need to define two mutually disjoint closed subsets suitably. We consider B1, which is a set of all X element of A for which f of X is less than or equal to minus 1 by 3. And define C1 as the collection of all X element of A satisfying the relation f of X greater than or equal to 1 by 3. Then it is obvious that B1 and C1 are mutually disjoint. Also, we can see that B1 can be expressed as the collection of all X element of A for which f of X belongs to closed interval minus 1 by 3, since the codomain of small f is closed interval minus 1 plus 1. Therefore, we can express B1 as the inverse image of the closed interval minus 1 by 3. And we know that the closed interval minus 1 by 3 can be expressed as the intersection of the subspace minus 1 plus 1 and some closed set, say minus 1 by 3, the closed interval itself. So this is in fact the intersection of a closed subset in R and the subspace closed interval minus 1 plus 1. So this intersection will be a closed subset of the subspace closed interval minus 1 plus 1. We have expressed B1 as the inverse image of a closed subset of the codomain of F. Hence, this B1 will be closed in A. But A is a closed set of X and B1 being a closed subset of the subspace A can be expressed as the intersection of some closed set, say D1 of X and our subspace A. So we can see that B1 is in fact the intersection of two closed subsets of X. Therefore, B1 should be closed in X also. So B1 is a closed subset of the subspace A and B1 is also closed in X as well. Similarly, we can argue that C1 is a closed subset of X by expressing C1 in the form F inverse of closed interval 1 by 3, 1. And using similar arguments, we can conclude that C1 is a closed subset of the subspace A and of X also. Thus, we have proved that B1 and C1 are closed subsets of A and hence of X, since A is closed in X, and we have also seen that B1 intersection C1 is equal to 5. Now, we can apply Urysohn's lemma to these two closed sets. So we can construct a continuous function h from X to unit interval such that it is continuous, and h of B1 will be equal to singleton set 0 and h of C1. Every point of C1 is mapped to 1. Now we consider another closed interval, say minus 1 by 3 plus 1 by 3. We know that these two closed intervals are homeomorphic to each other. So let us consider the homeomorphism, say h1 defined from unit interval to the closed interval minus 1 by 3 plus 1 by 3. Then h1 being homeomorphism will be a continuous function and it will be a bijection. We can also construct h1 in such a way that h1 of 0 is equal to minus 1 by 3 and h1 of 1 is equal to plus 1 by 3. So if we consider a new function k which is defined as h1 composition h, then k will be defined from x to closed interval minus 1 by 3 plus 1 by 3. Since h is defined from x to unit interval and h1 is defined from unit interval to this closed interval, so their composition will be defined from x to closed interval minus 1 by 3 plus 1 by 3. And we can also see that k of b1 will be equal to minus 1 by 3 since h maps every point of b1 to 0 and h1 maps 0 to minus 1 by 3. The image of each point of b1 under k will be equal to minus 1 by 3. Similarly, we can see that k of c1 is also equal to 1 by 3 since every point of c1 is mapped to 1 by h and 1 is mapped to 1 by 3 under h1. So their composition will map every point of c1 to plus 1 by 3. So k of c1 can be expressed as singleton set 1 by 3. So we have constructed a continuous function defined from x to closed interval minus 1 by 3 plus 1 by 3 such that the first closed set b1 is mapped to minus 1 by 3 and c1 is mapped to plus 1 by 3. Let us label this new function as f1 for convenience. So we can see that by a variation of Urysohn's lemma, there exists a continuous function f1 from x to closed interval minus 1 by 3 plus 1 by 3 such that f1 of x is equal to minus 1 by 3 for all x element of b1 and f1 of x equal to plus 1 by 3 for all x element of c1. We can observe that for every x element of a, the absolute value of f of x minus f1 of x is in fact less than or equal to 2 by 3. Since if we take any x element of a, there are three possibilities. First possibility is that x may be a member of b1. There is another possibility that x belongs to c1. And the third possibility is that x is a member of a minus b1 union c1. In the first case, f1 of x will be equal to minus 1 by 3 since f1 maps every point of b1 to minus 1 by 3 and using the definition of b1, we can say that f of x is less than or equal to minus 1 by 3. So, f of x is less than or equal to minus 1 by 3 and f1 of x is equal to minus 1 by 3. So, f of x will be in the interval minus 1 by 3 and f1 of x is equal to minus 1 by 3. So, the distance between these 2 points f of x and f1 of x will be at most 2 by 3. Similarly, when x belongs to c1, we can observe that f1 of x is equal to plus 1 by 3 and f of x is greater than or equal to 1 by 3 using the definitions of f1 and c1. Here also we can observe that f of x minus f1 of x has an absolute value less than or equal to 2 by 3. Here f of x will be a member of this subinterval and this is equal to f1 of x. So the difference, the distance between f of x and f1 of x will be at most 2 by 3. That is the length of this subinterval. Now for the third case, since x does not belong to B1 and x is not a member of C1 also, so f of x will belong to open interval minus 1 by 3 plus 1 by 3. And we know that f1 of x will belong to closed interval minus 1 by 3 plus 1 by 3 since the codomain of f1 is this closed interval. Since the length of these two intervals is 2 by 3, the distance between f of x and f1 of x will be at most the length of these intervals, which is 2 by 3. So in all the three cases, we have seen that modulus of f of x minus f1 of x is less than or equal to 2 by 3. Now, we define another function g1 on a by g1 of x equal to f of x minus f1 of x. Then, the range of this function, this new function will be obviously closed interval minus 2 by 3 plus 2 by 3 using this property. So we can assume that g1 is defined from a to the closed interval minus 2 by 3 plus 2 by 3. Then since both f and f1 are continuous, g1 will be continuous. Now we apply the earlier argument to g1 instead of f. We will be defining two closed sets, say B2 and C2, using the following definitions. B2 is defined as the collection of all x element of A for which g1 of x is less than or equal to 1/3 of this number, that is minus 2 by 9. And similarly, C2 is defined as the collection of all x element of A for which g1 of x is greater than or equal to 2 by 9. Using appropriate variation of Urysohn's lemma, as we have seen earlier, we will be getting a continuous function f2 from x to closed interval minus 2 by 9 plus 2 by 9, which maps b2 to minus 2 by 9, this limit, and c2 is mapped to 2 by 9. Here we can prove that for every x element of A, modulus of g1 of x minus f2 of x, which is also the same as modulus of f of x minus f1 of x minus f2 of x, will be less than or equal to 4 by 9. Hence, we get a continuous function, a new continuous function g2 defined from A to the closed interval minus 4 by 9 plus 4 by 9, defined by g2 of x is equal to f of x minus f1 of x minus f2 of x. So, as f1 and f2 are all continuous functions, this new function g2 will be continuous. We repeat the same argument for g2 to get another map, say f3, which is defined from x to closed interval 4 by minus 27, 4 by 27, such that for every x element of A, g3 of x will belong to closed interval minus 8 by 27 plus 8 by 27, and g3 will be defined as f of x minus f1 of x minus f2 of x minus f3 of x. Continuing in this manner, we will be getting a sequence of continuous functions fn, which are all defined on x and which satisfy the following properties. First one, fn is continuous for each n element of n. Second property, modulus of fn of x is less than or equal to 2 raised to n minus 1 by 3 raised to n for all n element of n and for all x element of n. Here we can observe that modulus of f1 of x is less than or equal to 1 by 3, which can be expressed as 2 raised to 0 by 3 raised to 1. Similarly, we can observe that for f2, its absolute value can be expressed as less than or equal to 2 by 9, which can be written as 2 raised to 1 by 3 square. Similarly, we can see that we have constructed f3 in such a way that modulus of f3 of x less than or equal to 4 by 27, which can be expressed as 2 square by 3 cube. So the sequence fn will definitely satisfy this relation. Modulus of fn of x less than or equal to 2 raised to n minus 1 divided by 3 raised to n. The third property is that modulus of f of x minus sigma I varying from 1 to n fi of x is less than or equal to 2 raised to n by 3 raised to n for all n element of n and for all x element of a. In this construction, we have already observed that modulus of f of x minus f1 of x is less than or equal to 2 raised to 1 by 3 raised to 1. Similarly, we have already observed that modulus of f of x minus sigma I varying from 1 to 2 fi of x is less than or equal to 4 by 9, which can be expressed as 2 square by 3 square. Similarly, we have already observed that modulus of f of x minus sigma I varying from 1 to 3 fi of x is less than or equal to 8 by 27, which can be expressed as 2 cube by 3 cube. Thus, we can see that every term of this sequence fn will satisfy all these three relations. Now, we can see that the series sigma n varying from 1 to infinity 2 raised to n minus 1 by 3 raised to n is convergent, since this is a geometric series with common ratio 2 by 3, which is less than 1. So this series is convergent. By a proposition, we know that if sigma mn is a convergent series and if sequence fn is a sequence of real valued functions on a space x such that modulus of fn of x is less than or equal to mn for every n element of n and for every x element of x, then the series sigma fn will converge uniformly to a real valued function on the space x. Here instead of mn we have 2 raised to n minus 1 by 3 raised to n. Hence, by applying this proposition, we will get a uniformly convergent series sigma fn, which converges to, say, another function capital F on x. But we know that each fi and hence each partial sum of this series Sn equal to sigma I varying from 1 to n fi, each partial sum is continuous. So, by a previous proposition, this limit capital F is also continuous. From statement 3, we have f of x minus partial sum is bounded by the quantity 2 raised to n by 3 raised to n, but the real number 2 by n whole raised to n tends to 0 as n tends to infinity, and hence the sequence of partial sums Sn of x will converge to f of x for every x element of a. That is, sigma fn of x will converge to f of x for every x element of a. But we have assumed that the series sigma fn of x converges to capital F of x for every x element of capital X. Hence, we must have these two limits, capital F of x and small f of x are the same for all x element of A. That is, we have proved that capital F of x is in fact an extension of small f. And we have already proved that capital F is continuous. Thus, we have proved that small f has a continuous extension, which completes our proof.